Okay, so I made a video to do a review of polar coordinates. This is a topic that you learned about in trig, and we're going to pick it up again and talk about how to do calculus in polar coordinates. But first, I just want to do a review of some of the basics. So coordinates in general, that's a way that we assign numbers to a geometric idea. And what we've been doing in our class so far, we've been using x, y coordinates. Those are also called Cartesian coordinates, after one of the first people who worked with them. That's the mathematician René Descartes. Here's an example of plotting a point in Cartesian coordinates. So I have xy equals 2, 4. And when we do this, we go over to the right. That's the x coordinate. And then we go up for the y coordinate. Now we're going to look at another way to assign numbers to points in space. This way is called polar coordinates. Again, we have two coordinates. Here they're called r and theta. And when we graph a point in polar coordinates, we start by looking at the angle. That's the coordinate theta. So theta equals 0 is the direction of the positive x-axis. And then whatever value we're graphing, we turn counterclockwise by an angle theta. And that gives us a direction. I've done an example here. I'm plotting the point r theta equals 3 comma pi over 3. So I start by turning counterclockwise an angle of pi over 3 radians. That gives me the dashed line that's shown on the graph. So for the next step, we use that line as our direction, and we go straight out along that line a distance r. In this example, r is 3. So I moved out along that line 3 units, and then I plotted my point where I ended up. You can see the results on the graph. Okay, I have a couple other problems, just some polar coordinates that I want to plot. This is the kind of thing that you'll be doing on the homework. So my first point, point A, I have 2 comma 3 pi over 4. I start by turning counterclockwise an angle of 3 pi over 4 radians. And then I go out a distance of 2 units, and so point A is that point that's shown on the graph. For our second point, we have an angle of 3 pi over 2 radians. This is going to put me on the negative y-axis. So I go down 2 units on the negative y-axis, and point B is the point that's shown. For point C, we have something a little different. Notice that the radius is negative on this point. So again, I start by turning an angle of 3 pi over 4 radians counterclockwise. That gives me that line. And now I have to go a distance of minus 3 units along this line. The way that we interpret that minus 3, we go backwards 3 units. Okay, so the direction given by my line, I move backwards 3 units, and that gives me the point that's shown on the graph. In our final example, we have a negative angle. So for that angle, negative 3 pi over 4, I start by turning clockwise instead of counterclockwise. I turn negative 3 pi over 4 radians, then I go out a distance of 4. And so the final point in this example is what's shown on the graph. That's the way we plot points in polar coordinates. The next problem we're going to talk about is converting a point between its Cartesian form and its polar form. And this is where the relationship to trig comes in. So the quantities that we're working with are described by the following right triangle. That's something you've seen before. And remember that this works because the x direction and the y direction in our familiar coordinate system, they make a right angle. So that triangle that I've drawn there is a right triangle. And we're going to be able to describe it using functions from trig. All right, first form of the problem. Let's say that we're given the polar coordinates and we want to find the equivalent xy coordinates. The formulas that I'm going to use to do that are shown there. And those just come from the definition of our trig functions, sine and cosine. So I use the ratios from SOHCAHTOA to set them up, and then I solve for x and y. Let's take a look at a specific problem. So here we're given the polar point 2, 5 pi over 4. And I want to convert that to its equivalent Cartesian form. Before I do that, I'm going to plot the point. It's useful to do this to check your work and make sure that things are coming out the way that you expect. So here's the polar point 2, 5 pi over 4. And now I'm going to use the formulas that we saw in the last slide to derive the equivalent Cartesian coordinates. Here's the formula for the x-coordinate. Next, I'm going to plug in the values of r and theta that we were given in this problem. That's shown there. The cosine of 5 pi over 4 is an angle that we're familiar with. So that cosine minus root 2 over 2. My final answer simplifies down to just minus root 2. Similar set of steps for the y-coordinates. There's the formula. We're going to plug in the values for r and theta that we were given, and then simplify. So now we have our answer. The x-y coordinates of the point that we're looking at are minus root 2, minus root 2. Now for my last step, I'm going to check my work by graphing. So I graph the x-y coordinates that I just found. I want to check and make sure that that matches the original picture that I got when I graphed the polar coordinates. If you go back and check, you'll see that this is a match, and so the work that I've done seems to check out. Now I want to talk about doing that problem in the other direction. So let's say that we are given x, y coordinates, and we want to find the equivalent polar coordinates r and theta. Again, we're going to use a right triangle to do that. So I'm given my x, y. I get r from the Pythagorean theorem. R is the hypotenuse of the right triangle. And then to find theta, I'm going to use this relationship. So I know that tangent of theta equals opposite over adjacent. In this problem, that's just y over x. So the definition of tangent is opposite over adjacent. There's another way that we can look at that same idea. Tangent is also the slope of the line that we're looking at. So remember, delta y over delta x is a slope, and that's the same formula that's giving us the tangent. We're going to need to do one extra step to identify theta. And this is because that equation that we're working with has two solutions on the unit circle. And these are two distinct angles. They're not just the same angle separated by multiples of 2 pi. I've drawn a picture of that idea here. So remember that the tangent is the slope of the line. If we have a line y over x, then you can see that that line is going to cross the unit circle in two places. So those are the two solutions to the equation tangent theta equals y over x. Another way to look at the same idea is to look at the graph of the tangent function. Here's a graph of tangent theta. And remember that at this point in the problem, we've been given numbers for y and x. And we're looking to find solutions. We want to solve the equation tangent theta equals y over x. Y over x is just a number in this problem. For example, we could take y over x equal to 3. And then that would give us this horizontal line on the graph. The solutions that we're looking for, points where the line crosses our curve for tangent theta. And we see there are, in fact, multiple solutions. And more than that, there are two solutions between 0 and 2 pi. So two fundamentally different solutions to this equation. Okay, that's a picture of our multiple solutions. Now I want to look at how we can calculate these solutions using algebra. The first solution that we're going to look at comes from the inverse tangent function. So the equation tangent theta equals y over x. We can take the inverse tangent of both sides, and then we get theta equals inverse tangent y over x. This is one solution to our problem. And this function always gives us an angle between minus pi over 2 and pi over 2. So that's the first solution that we're looking for. The other solution, it's going to lie on the opposite side of the origin. And so the way we identify an angle for this solution, we're going to add pi to the value that we found on the last slide. Here's a picture of how those two solutions are lined up. So notice that they're on the same line, they're on opposite sides of the origin. The way that I move from the first solution to the second solution is by turning an angle pi, 180 degrees or pi radians. So we see that the two solutions we're looking for are related by the angle pi, and we can use this to update our formulas for finding polar coordinates. The work that I just did translates into these two formulas. So we have one formula for r, that's the same thing that we saw before. But now we've rearranged our equation for theta. We have two possible equations for theta. The possibilities are separated by pi. And if we're finding the coordinates of one point, we're always going to choose one of those angles, but not both. All right, let's see how this works on a specific example. So here's a point. We're given this point in xy coordinates. It's -1, 1. And we want to find the equivalent polar coordinates. Just like the last problem, I'm going to start by plotting my point. I'm going to use this to check my work after I complete my calculations. First, let's calculate the value of r. Here's the formula that we use to do that. Plug in the x and y coordinates that I'm using in this example, and then I simplify it. So r is equal to √2. Now we're going to work with theta, and I'm going to look at the two formulas that I have for theta. There they are. Again, we're going to plug in the y and x values that we were given in this problem. Simplify. And then we know the inverse tangent of -1. That's -pi/4. So these two formulas give me two possible angles, -pi/4 and 3pi/4. We're going to make a graph of both of these possibilities, and we're going to compare it to the location of our point. Remember, we were given our point in xy coordinates. First angle I'm going to look at, -pi/4. So there's the angle -pi/4. There's the point that we're plotting. And you can see that in this case, they're not a match. The point that I'm plotting does not lie on the angle that we're looking at. So now I'm going to try the other angle that we found. That was 3pi/4. When I compare the graph of this angle to my point, I see that I have a match. And that tells me that for this point, the polar coordinate theta is 3pi/4 radians. Here's a summary of the work that we did on this problem. So I converted my Cartesian coordinates to the equivalent polar coordinates, √2, 3pi/4. So that is how you move back and forth between the two coordinate systems that we're talking about. Next problem we're going to look at is graphing solutions to an equation that's given in polar form. I want to look at this in terms of an example. So we're going to see how to plot the solutions of r equals 1 plus cosine theta. There's a couple ways that we're going to do that. First, we're just going to start by making a table. So I'm going to pick values of theta, put them in my table, and then for each value, I'm going to plug it into the formula, get the corresponding value of r, and then I'm going to plot all the pairs that I have in my table. So here's the first value of theta. I'm going to start with theta equals 0. I'm picking values of theta that are easy to work with. Then I plug that into my formula. Remember, we're plotting 1 plus cosine theta. And for this value, the corresponding r coordinate is 2. We're going to do the same thing. We're going to pick enough values of theta to get a good picture. So the next value that I analyzed was theta equals pi/6, and that gave me r equals 1.9. I keep doing the same thing. So here are the values in the first part of my table. Now I'm going to plot each of those points. We talked about how to plot these points a few minutes ago. So for the values you see in the table here, those points go on the graph as shown. All right, I'm not done. I need enough values of theta to cover the whole circle. So here I pick some more values of theta, use my formula to get the equivalent values of r, and then the second group of points in my table go on the graph as shown. I'm going to keep going. So for the next quadrant, I picked some values of theta, calculated the corresponding values of r, and put them on the graph. And then I finished up by doing the following table of angles. Again, I found the coordinate r and plotted them on the graph. So now we have enough points to get a picture of what this curve is doing around the whole circle. I'm going to think about just connecting these dots with a smooth curve, and the result looks like this. So that was a graph of a polar equation. I've got a couple problems like this that I'd like you to try before class. And the next time that we meet, we're going to talk about doing calculus on curves that are expressed in polar form.